Okay, hello everyone. So this video is regarding a better derivation of the pseudo forces when there is a 3D. I mean there is a the- I mean here the angular velocity vector is not fixed to one particular z-axis, but rather it is a general 3D vector. So this derivation is more general to see how in the rotated frame, how in the rotating frame, the acceleration, how are the accelerations. If we know the acceleration in the non-rotating frame, then how does the accelerations are there in the rotating frame. So it is also a motion in rotating frame, and I have made one video on this, but there it was more of a hand wavy physics. I mean, not hand wavy exactly, but it was more of like I proved some result for the omega and z axis, and then I basically extended the result in general. But that is not really the the best way to do physics. The best way to do physics is to do in generality as far as possible. So I have one general derivation in mind which I want to do here. So the scenario is such that let me use different color. So we have the three axis, and please forgive me if for the my hiccups or I mean for the over enthusiasm here because I did this derivation on my own and it took me some time, really it took me some time to do it on my own. I used different approaches to proceed, but then I found the most easiest approach to do this. So actually I'm a little bit excited, so please bear with me. So this is my uh, coordinate system E1, E2, and E3, and this is the omega vector. So around this general omega vector, now notice that this omega vector is not along the E3 direction or Z direction or any particular axis. It is in general inclined in a general direction. So now this whole coordinate system is rotating about this axis with this angular velocity omega, right? So that's why it is a more general derivation to do things, and I really like it. Okay, so now these vectors, they basically, these basis vectors, they will move or they will rotate. So just to give you a sense of the rotation, so basically the E3 vector would be some E3 prime here, and the E1 vector would be rotated something like E1 prime, and obviously the E2 vector will be rotating E2 prime. So this is how the vectors are will be after some time. So the primes denote the new coordinate axis, right? Because of the rotation. So this is the definition of the primes. Now, what we want to do is that let's say we have the position vector r in the unprimed frame. So these red coordinate axes are the unprimed and the pink ones are the primed. So the in the unprimed we can simply write it as xi and ei, right? This is r, what is r? R is the position vector of a particle. Okay, so there is a particle here. Let's say a particle is moving like this. So this is particle p. So you extend one vector, which is your r vector, right? And this you can do both in prime frame as well as in unprimed frame. So okay, so let me just remove this thing because otherwise it will clutter a lot, which I don't want obviously. So I will just remove it. So this is the r vector. So r vector is the basically it's the position vector of particle, right? And from here we can also write it in an unprimed form. So a vector doesn't change. Either you go in primed or unprimed, it doesn't matter. The vector doesn't change. So in primed, then we can write it as something like x prime I and e I prime. So the vector is same, but now here the coordinate system is this primed one, the pink one. Okay, so if you're comfortable with this fact, now I want to know the how does the velocity transform. So once we know how velocity transforms, the rest of the derivation can be done in fairly, I mean, easy manner. So that, I mean, I will not do the whole derivation again because I did this for once. I did this once. So I will just do this whole 3D thing for only the velocity transformation. Acceleration I would really encourage you guys to do on your own. Okay. So let's take the derivative to see how the velocity is transformed. So let me just write this expression here, and now just let me just take the time derivative. So dr by dt. So because again these primes are not fixed in space, they are rotating. So this whole thing is going on and on and on. They are rotating, right? So I have to take the derivative, time derivative with respect to both. So I have to apply the product rule for the differentiation with respect to time. Now this dr by dt, this is just the particle position in the unrotated frame. So this is just velocity vector in the unrotating frame. And what is this exactly? So this thing here is the how does the coordinate ith coordinate of the particle changes with time and expanded in terms of the basis vector. So again, I reiterate, I think the thing is that this I and I, these are dummy indices, which means that they are being summed over. So you can write this as 1, 2, 3 also. But in my notation, I follow the Einstein summation, so we don't explicitly write here. We simply, whenever the index is repeated, we understand that this is a summation. Okay. So this thing here is basically velocity vector in the rotating frame. Why? Because this is the change of coordinate with respect to time and then expanded in the prime frame only. So these are the basis vector in the prime frame. So this is the velocity vector in rotated frame. But the most interesting quantity out here is this one. So what is this? We need to figure this out here. So what is the time derivative of these rotating basis vectors, right? So what we do here is that this rotating, so this rotation is in, this is a general rotation about this omega vector. So what we want to do is basically we want to split up this e prime I into two components, and which two components? Components that is along this omega vector and component which is perpendicular to the omega vector. Okay. So what I'm going to do, I can write this e prime I is equal to something like E prime perpendicular, right, plus E prime parallel, something like this. So this is what? This is perpendicular to what? Perpendicular to omega vector, and this is parallel to omega vector. Okay. We have this choice of splitting. We can split it up, right? So if we split up this, what is the point of splitting? See, the thing is, the thing to realize is that the component which is parallel to the omega vector, this component isn't rotating at all because it is along the axis of rotation. So when the component is along the axis of rotation, it is not rotating. Only the component which is perpendicular to the axis of rotation, only that component is only that contribution only I mean only that component is the contributing factor here. So that's why when I differentiate this thing, so it would be d by dt of ei perpendicular prime perpendicular plus d by dt of e prime parallel. So I'm putting prime here. Let me just rewrite this thing, right? Something like this. So don't be confused. This is parallel and this is just prime. So anyways, this factor is going to be 0 here because this is a component parallel to the axis, rotation axis. So we can write this expression. So now our problem of determining the expression here is reduced to finding d by dt of this perpendicular component, right? So let me just make one diagram for this for better understanding. So let's say our omega is like this. Let's say my omega is this. What is the perpendicular component? Perpendicular component lies in this plane which I am making here. So let's say that this is my perpendicular component. So this is my EI perpendicular prime, right? But this EI perpendicular prime is not sitting quietly, it is rotating in this plane. So it is rotating in a circle. It keeps on rotating in a circle. So maybe I can use a different color to denote the rotation here. So this is rotating like this, right? So this vector is rotating in a circle, full circle. So we want to determine its rate of change, which is fairly simple, isn't it? So we have a vector which is rotating in a circle, and what we are asking? We are asking what is the rate of change? What is the rate of change, right? So let's say, so I'm making this circle here. I'm making this circle here in a different color. So this is my circle. This is my circle here. Let me just write it in red only because then it will the color coding will be, I mean, consistent. So this is my circle here. So this is the circle here. So let's say my vector starts from here, right? So this is, let's say, at time t1, this was my E perpendicular I. So let's denote this thing as EI perpendicular prime at t1, right? And then it rotates like this, and the vector goes here. So this vector is EI perpendicular prime at t2. So what we are interested in, or what we want the derivative. So what is the derivative? So d by dt. So this is I. This would be what? This would be perpendicular I at t2 minus E vector perpendicular prime at t1 divided by delta t. Well, we can do better. We can do better in terms of, let us not write this thing here. What we can do? So instead of putting the constraint on time, we can put the, because this is changing with angle, right? And angle is changing with time. So this is some delta theta. This is some delta theta. So this expression here we can write as del EI perpendicular prime by d theta, and then this should be d theta over dt, right? This we can write. So this thing would be omega times del EI perpendicular over del theta. So we just want to see what is the theta derivative. How does it changes with theta? That is easy to see, I mean, directly, right? So with theta, so we want to evaluate this expression here. So this expression would be EI perpendicular prime by delta theta. This would be simply EI. So let's say that here this is my theta 1, this is my theta 2. Okay, so instead of putting as a function of time, we can also put this as a function of theta. So you can do as a function of time, I mean, whatever you want, it is changing with time eventually, but I prefer this thing here. So I think it is little bit misleading. So this vector here, this vector is basically EI perpendicular prime at theta 1. And this vector here is the at theta 2, right? And the difference theta 2 minus theta 1 is delta theta. I hope it is clear now. So this would be perpendicular prime at theta 2 minus E perpendicular prime I theta 1 divided by delta theta, correct? So what is this? As delta theta goes to 0, so obviously there is a limit here that delta theta goes to 0. That is the I mean that is the basic definition of the differentiation. So as this delta theta goes to 0, they come closer and closer, and you can observe geometrically. Geometrically, you can see that as this moves closer, so the derivative would be in this direction, right? It is tangential, which is not new because from the circular motion, you know that velocity is tangential, right? Tangent to the circle. So you know that the velocity vector goes in this direction, right? So it is not a very, something not very new. It's very old fact. So, but what really matters here is the magnitude. So we have to figure out the magnitude correctly, and that is the whole point here, right? So this is just subtraction of two vectors. So we know its direction, right? So let us just write it as like it would be mod of this quantity and times some direction here, right? So direction, I think we already know, right? We know the direction. Direction is tangential, like this, tangent to the circle. So here, if you want to show the direction, it is here. So this is the direction. This is the direction for the del I perpendicular prime by del theta, right? But what is, can we represent this direction using the omega and EI perpendicular prime. Just think about it. So it is indeed very possible, and we can represent this as a cross product of omega vector with EI prime. But notice we have to take the unit vectors here, because here this, if you want to represent this direction, it should be a unit vector, right? So the direction should be something like omega cap, which is the unit vector of omega vector along the omega vector, and cross it with the EI, and here I just messed up with the notation. This is the correct notation: perpendicular prime cap. So this is, so I'm putting cap on both the, on both the directions. Maybe no. This is incorrect way to do it, because what I want here is something, a unit vector. What I want here is a unit vector, because this is mod and a unit vector should be there. So it should be better to represent it like this. So we take the uh, cross product as it is, and then we divide it with the mod. So this will make sure that this quantity here is a unit vector. Let's make sure that this is a unit vector, correct? Okay, so what is going on here exactly is that del I prime perpendicular by del theta. So what is the magnitude? We need to figure out this magnitude, and we have to do it geometrically. So we know that if the, so I need to draw one diagram here. So basically this is my EI perpendicular at theta 1. This is my E I perpendicular at theta 2, and we want to subtract, so this is the subtraction vector here. And what is its magnitude? So the magnitude here, so this quantity here would be under root of a, I mean, if you have two vectors, you subtract it, so it will be simply mod of EI perpendicular prime, because mod here is not changing, only the direction of this vector is changing. So you can write mod of this thing here, mod square, plus again, so I mean, just to be complete with notation, square plus 2 mod EI perpendicular prime theta 1, right? And mod EI perpendicular prime. I'm really carrying this notation for too far now. So this delta theta is the angle between them. So obviously cos of delta theta. So this result is from simple addition of the two vectors. I think I missed here one minus. So because it is a minus here, so it should be minus here, right? Because we are subtracting the two vectors. So should be able to say it correctly. So the mod EI perpendicular prime at theta 1 is equal to this same quantity, and let us call it just A. Let's call it A for our purpose. So the quantity here, mod of this thing, oh sorry, this notation is really sorry, this notation is really making troubles now. I should have simplified it, but let's just deal with it now. We can do correct it now. So let's say this is a square plus a square, and this would be minus 2a square cos delta theta. You can notice you can take a square out, or rather 2a square out, so it will be root 2a, and this would be simply 1 minus cos of delta theta. It is not very difficult to see that this thing will be under root of 2 sine square delta theta by 2, correct? Now we can use this fact that delta theta is goes to 0, so sine of delta theta by 2 is simply delta theta by 2, and there is a square, so it will be squared, so root 2a, and under root 2 into this will be delta theta square by 4, so this 2 into cancels, and this root 2 cancels, so what remains is a delta theta. Okay, so far so good. And this is the differentiation here. I think I missed uh, something. Okay, fine. So actually, the thing is that this is the so when I write the differentiation, so differentiation is basically the subtraction of the two vectors. So it will be magnitude of subtraction, and it should divide also by delta theta. So everywhere it is dividing by delta theta, divide by delta theta, divide by delta theta. So here also it divides, gets divided by delta theta cancels. So we get EI by modulus of this thing is simply A. So what is A? So A is simply the modulus of this quantity. So you see that this perpendicular prime component, this whatever this is, it is the differentiation just comes out to be the modulus of this quantity. So that is a very simplified result. So we have figured out what the mod is. Now we want to figure out what this quantity exactly is. So let us just write, let me just switch to the green now. So del E perpendicular prime by delta theta would be simply mod of EI perpendicular prime at any theta. So this mod is independent of this mod is modulus of this vector is constant because it's rotating. So it doesn't depend on the theta. So we can just remove this theta here because it is not a function of theta anymore. So this would be omega prime EI, this quantity here. Oh, sorry, this is a mod. Okay, so we can write this mod in a better way. Should be able to write in a better way. So one thing we realize here is that we can write this omega cross this thing as omega mod of omega, right? And mod of this thing here into the angle between omega and perpendicular. But by definition, when we are saying that this perpendicular component is perpendicular to the omega vector, so the sine of 90 is just 1. So it will be simply the sine of 90, right? When we want to write the mod, cross product is mod A mod B sine theta. Sine 90 is 1, and this thing here is I perpendicular prime here. So this thing here simply cancels, right? And then only the omega, only this thing remains, and 90 is 1. So we are pretty much done with our derivation now. So we can write d by dt of e prime is equal to, so we just go back here. So this is just omega times in this quantity. We have figured out this quantity in the bracket. It will be simply omega into this quantity which we have right now derived. So it will be omega cross E perpendicular prime I divided by omega again. So mod of omega vector just omega. So omega cancels here, and then we just write the differentiation of the derivative of this basis vector, general basis vector. Now it is no more the perpendicular component. This is the full general basis vector. So its time derivative is simply omega cross EI perpendicular prime. Okay, so we have reached this stage. Now let us just substitute this thing. So why we are doing all this? Because we were stuck at this equation here. So we do not know earlier what is the derivative. Now we know. We just write there, substitute it there. So it will be u vector particle velocity in rotated frame is equal to particle velocity in the rotated frame plus x prime I, and then we substitute this one here as perpendicular prime I, right? And this summation is over I here. Now we can play out a very simple trick here. We know that we know because we know that the omega cross EI parallel prime is equal to 0 because cross product when the parallel component is there. So what is parallel component is if this is omega and the parallel component is along, right? That's why it is called parallel. That is the definition. So the vectors are in the same direction. So that means their cross product has to be zero, right? So we know that this cross product is zero. We can simply add that thing here. So we can write this equation as x prime I and omega, and we can add this thing here. EI perpendicular prime was already there, but now we can also add the parallel prime. We can sneak in the parallel component here because the cross product is zero. That is something that is good trick here, right? Small trick. So now we can simply write this thing as x prime I, sneak in the x prime I, and all this is done because of a reason which you will realize now. Because this x prime I and ei prime perpendicular plus ei prime parallel, so when you add this thing, this is just ei prime itself, right? So you realize that this thing here is x prime I and ei prime, right? And summation, obviously there is a summation. So this, what is this thing here? This is just r vector, isn't it? This is r vector. So this is omega cross r. So the particle velocity in the unrotating frame is equal to the particle velocity in the rotating frame plus this omega cross r. So now we have derived this omega cross r in a very general sense, where this omega vector was originally, it was taken to be in a general three-dimensional direction. So this derivation is a general derivation, right? I did not assume anything. I did not write any explicit forms about the basis vector. This is pure general expression, right? So I really liked this derivation, and I was really excited to recall this. So I'm very happy that I was able to derive it. Now, if you want to find out what is the acceleration, so you just differentiate it once more here. So I will not do the whole derivation now because you got the idea how does the basis vector transform. That is the whole point here. So you will be able to do now everything. So this will be d omega by dt vector cross r plus omega cross dr by dt. Now the point here is that this thing also can be broken like, okay, just 1 second. I need to stop this. Okay, I think I'm not able to stop. There should be some command, but I'm just going to finish this video anyways. So now you can just take the derivative here and then represent this rotation thing as, like, you can write this in the rotating field, write this as u I prime into e I prime, something like this, and then again take the derivative, and then now you know how this the derivative of this is, uh, it goes, right? So that's how you can finish the derivation. So bye.